Hello everyone. This is an assignment on use of ICT in education for online and blended learning. In this module, we will talk about AC parallel circuit. AC parallel circuits. Impedances in parallel add together like resistors in parallel. These impedances must be added vectorially. Whenever a capacitor and an inductor having equal reactances are placed in parallel, equivalent circuit of the two components is an open circuit. Now we will learn about some basic terms. First one is conductance, which is represented by the symbol G. It is a reciprocal of the resistance. Susceptance, which is represented by letter B, is the reciprocal of reactance. Admittance, which is represented by the symbol Y, capital Y, is a reciprocal of the impedance. Unit of all these are in units of for all of these is Siemens, which is represented by the letter capital S. In a parallel circuit, there are multiple pathways for a charge to flow. Current goes through each of the branch at the same time. Each device is placed on its own separate branch. In figure 4.1, there are two parallel circuits. In the first circuit, there are two paths for the current to flow, the first bulb and the second bulb. In the second circuit, there are three parallel paths for the current to flow. Parallel circuits, pros and cons. Advantages. The more devices or resistors in a parallel circuit does not decrease the current. So there is no question of dimming of bulbs. If one resistor breaks or bulb goes out, the rest do not. Hence the reliability of the system increases. But the problems are current does not stay the same for the entire circuit. So energy is used up quicker. So the total current increases equal to faster electrons equal to hotter wire is equal to fire. Okay, so here is parallel circuit resistance. Resistor added side by side. Here R1 and R2 are connected side by side. There are more paths, so the total resistance is lesser than R1 and R2. The equivalent resistance is given by 1 by R equivalent equal to 1 by R1 plus 1 by R2 plus 1 by R3, where R equivalent is the equivalent resistance of the whole circuit. Then since the circuit offers the two equal pathways for the charge flow, only half of the charge will choose to pass through a given branch. Figure 4.2 gives two resistors connected in parallel. Parallel circuit. Here all paths are used, but the charge divides up into all branches. One branch can have more current than other branch. Depends on resistor in branch. Total current is equal to sum of current in each path. So I total is equal to I1 plus I2 up to In, where n is the number of parallel paths. As we can see from the figure, there are two parallel paths. 2 ampere is flowing in each path. So the net current is equal to 4 ampere, which is equal to 2 ampere plus 2 ampere. Parallel circuit voltage. A charge only passes through a single resistor. Voltage drop across the resistor that it chooses to pass through must equal the voltage of the battery. Total voltage equal to the voltage across each individual resistor. So Vt is equal to V1 is equal to to Vn, where n is the number of parallel paths. So voltage across resistor R1, R2 and R3 will be the same for the figure 4.4. In this numerical, here we have given a numerical. In this numerical, there are two parallel paths. For one path, a 70 ohm resistor is connected in series with 60 ohm inductive reactance, and in the another path, we have connected a 40 ohm resistor in series with a capacitive reactance of 25 ohm, and these two are connected in parallel. So, how to solve such circuits? First, we need to find out the equivalent impedance of the whole circuit. So we will proceed by 1 by Z equivalent is equal to 1 by Z1 plus 1 by Z2, or ZT is equal to Z1 Z2 by Z1 plus Z2. Now ZT is equal to 37.69 angle 9.06 degree in polar form, or in rectangular form the same is equal to 37.22 minus 5.93 ohms. Parallel resonance. Parallel resonance and series resonance. Here we have compared the the phenomena of parallel resonance with the series resonance. Parallel RLC circuit. Like the series RLC circuit, we can solve this circuit using the phasor or vector method, but this time the vector diagram will have the voltage as its reference with the three current vectors plotted with respect to the voltage. The phasor diagram for a parallel RLC circuit is produced by combining together the three individual phasors for each component and adding the currents vectorially. So as voltage is same across resistor, inductor and capacitor, so the voltage Vs will act as a reference vector and the current IR, IL and ILC will be plotted according to this reference vector. And then the resultant of this vector IR plus vector IL plus vector IC gives vector IS, which is a total current flowing through the circuit, and this will be plotted with respect to the voltage vector Vs. In this figure we can see voltage V is plotted on the x-axis. The current IC will be leading the voltage by 90 degree. The current through the inductive reactance will by flowing with 90 degree lagging with respect to the voltage. So the net current will be equal to IL minus IC plus IR, which lags by angle theta with respect to the voltage. Impedance of a parallel RLC circuit: R is equal to V by IR, XL is equal to V by IL, or XC is equal to 1 by V by IC, where we are trying to find out R, XL and XC. So Z is equal to 1 by root over 1 by R whole square plus 1 by XL minus XC whole square, or 1 by Z is equal to the inverse of the previous expression, which is equal to root over 1 by R square plus 1 by XL minus 1 by XC whole square. Admittance triangle for a parallel RLC circuit. Admittance and impedance triangle of a parallel RLC circuit. In the first figure we have given impedance triangle. This figure is drawn for a parallel RLC circuit. So resistance is taken as the reference and reactance is drawn accordingly. So we have got the impedance vector. By taking the inverse, for drawing the admittance triangle, we have taken the conductors as the reference and we have drawn susceptance accordingly, and we have got admittance vector. So admittance Y is equal to root over 1 by R square plus 1 by omega L minus omega C whole square. Impedance, which is the inverse of admittance, is equal to 1 by Y is equal to 1 by the above expression. So the power factor cos phi is given by G by Y, and tan phi is equal to P by G. Here in this numerical we have connected a source which is connected in parallel to three components: a resistor of 50 ohm, an inductor of inductance 20 millihenry, and a capacitor of capacitance 5 microfarad. So how to find the total current? For finding total current, first we need to find out the inductive reactance. Inductive reactance XL is equal to omega L and omega L is equal to 2 pi F. So the inductive reactance XL is equal to 2 pi FL, which comes about 12.6 ohm. Capacitive reactance XC is equal to 1 by omega C. Omega here it is equal to 2 pi F. So XC is equal to 1 by 2 pi FC, which comes to around 318.3 ohm. So the impedance is equal to 1 by root of 1 by R square plus XL 1 by XC minus 1 by XL whole square, which comes about 12.7 ohm. So current through resistor IR is equal to V by R, 50 by 50, where as you can see 50 is the RMS value of the source voltage. So 50 by 50, which gives 1 ampere. The current through inductor, as we have noted earlier, that the voltage across parallel combination remains the same, so we will again be 50 by 12.6 gives 3.9 ampere, where 12.6 was the inductive reactance. So total supply current will be equal to is equal to root over 1 by R square plus IL minus IAC ka whole square, which gives 3.87 ampere. So conductance, admittance is measured and phase angle is found out to be 0.256. Current and admittance triangle is drawn accordingly. Thank you.